Hello and welcome to Controllers Tech. Today, we will continue with part 7 of the STM32 custom bootloader series. In part 6 of this series, we demonstrated how to flash an OTA update using Ethernet communication and verified the update process successfully. As mentioned in the previous video, today we will learn how to flash the update completely wirelessly by using the ESP8266 module, removing the need for wired network communication. In this project, I will also include an external flash memory to store the downloaded OTA update file, which will later be written into the internal flash memory by the bootloader. The overall process is quite simple and easy to understand. The application will first receive a trigger signal. After receiving the trigger, it will initialize the ESP module, download the firmware update from the server, and store the downloaded file inside the external flash memory. Once the system reboots, the bootloader will take control. It will then copy the firmware from the external flash into the internal flash memory, perform all necessary validation checks, and finally boot into the updated application. Since this project involves some new hardware components, let us first understand the complete connection diagram before moving forward. I have connected an ESP8266 module using an adapter board to ensure stable power and proper signal levels. The ESP is connected to UART2, where the TX pin of STM32 is connected to the RX pin of the ESP, and the RX pin of STM32 is connected to the TX pin of the ESP, allowing two-way serial communication between them. I have already covered the STM32 IoT series in detail, so if you want to understand the ESP8266 communication and configuration better, you can check that series from the link shown in the top right corner. I have also connected a W25Q external flash memory using the SPI interface. This external flash memory will be used to store the downloaded OTA firmware file before it is written into the internal flash of the microcontroller. The STM32F103C8 microcontroller has limited internal flash memory, and because of this limitation, using external flash becomes necessary to temporarily store the OTA update file. I have connected a USB to TTL converter to UART1. This connection will allow us to monitor debugging messages and logs through the serial console, which helps in tracking the update process and troubleshooting if needed. Additionally, I have connected a push button, which will be used to trigger the OTA update process on the microcontroller whenever required. There is also an LED connected to the board, which will indicate the currently running application and help in visually confirming firmware changes. I am going to continue this project from part 5 of this series, where we successfully flashed the OTA update using the OTA image.h file. Now, let us begin by working on the application project first. There are many features to be added in this project, so we need to update and modify the project configuration using STM32 CubeMX. First, open the application project inside CubeMX so we can begin updating the hardware configuration. Currently, UART1 is configured to print debugging logs to the serial console, and the PA1 pin is connected to the LED, which helps indicate the running status of the application. Now, let us configure SPI1 in full duplex mode, which allows data to be transmitted and received at the same time. This SPI interface will be used to connect the W25Q external flash memory, where the OTA firmware file will be stored. Make sure the data size is set to 8 bits, and configure the SPI so that the MSB, most significant bit, is transmitted first, as required by the flash memory. Next, configure the prescaler so that the SPI baud rate remains close to 1 megabit per second, which provides good speed while maintaining reliable communication. Also, verify that the clock polarity is set to low and the clock phase is set to first edge, as these settings are required for proper communication with the W25Q flash memory. The pins PA5, PA6, and PA7 are automatically configured as SPI pins, which will be used for the SPI clock, MISO, and MOSI signals. We also need a dedicated pin for the chip select signal. For this, configure PB0 as an output pin. After configuring the pin, rename PB0 to CS. Next, we need to configure UART2, which will be used for communication with the ESP module. The pins PA2 and PA3 are configured for UART2, and this is where the ESP module will be connected for wireless communication. Keep the baud rate set to 115200, since most ESP modules are pre-configured to operate at this speed by default. Now move to the DMA settings, and enable the RX DMA for UART2 to improve data reception efficiency. Configure the DMA to operate in circular mode, which allows continuous reception of data without needing to restart the DMA repeatedly, and make sure the data width is set to byte for proper data handling. Next, go to the GPIO settings, set the PB0 output speed to high, and also configure the initial output level to high to ensure the chip select pin remains inactive until it is intentionally driven low. That completes all the required configuration inside CubeMX. Now click Save, which will generate the updated project files with all the new settings applied. Now, the first step is to copy the required library files into the application project. These files include the previously used libraries, which have been slightly updated, along with new library files for the ESP8266 module, and the W25Q SPI flash memory. You can download all these files as part of the complete project package using the link provided in the description of this video. Let us go through these files one by one, starting with the ESP STM32 header file. Inside this file, you need to define the WART instance that will be used for communication with the ESP module, ensuring that the library communicates with the correct hardware peripheral. Next, you will find an option to enable or disable debugging logs. Although this is optional, I strongly recommend keeping the logs enabled because they help in monitoring communication and troubleshooting any issues during development. Now, move to the W25Q source file. In this file, you need to define the SPI instance that will be used to communicate with the external flash memory module. You also need to specify the flash memory size of the module in megabits so that the library can correctly handle memory operations and addressing. The chip select pin has already been configured earlier in CubeMX, so there is no need to modify or define it again inside the library. Next, we move to one of the most important files in this project, which is the ESP source file. This file is responsible for handling all communication and control related to the ESP module. At the beginning of this file, you need to define the SSID and password of the Wi-Fi access point that the ESP will connect to for internet or network access. After that, you need to define the IP address and port number of the TCP server that will send or push the OTA update to the device. In this example, I have used the IP address of my computer because the TCP server is running locally on it. We will not go into detailed explanations of every function in this file to keep the video focused and easy to follow. Most of the functions are already well commented, so you can study them later if you want to understand the internal working in more detail. The main function that starts the OTA process is OTA start. This function is responsible for initiating the complete OTA update sequence. It first initializes the ESP module, and then connects it to the configured Wi-Fi network using the provided credentials. Once the module is successfully connected to the network, it establishes a connection with the configured TCP server, initializes the W25Q external flash memory, and finally sends a start command to the server to indicate that the device is ready to receive firmware data. The next important function is ESP OTA task. This function continuously checks whether new data has been received by the ESP module, and therefore it must be called frequently inside an infinite loop to ensure smooth data handling. Whenever new data is received by the ESP module, this function calls OTA process Rx to process the received data. The data received by the ESP8266 usually includes extra characters such as incoming packet data along with the actual firmware data, so we need to extract the valid data portion first before processing it. The OTA process Rx function performs this extraction and prepares the actual firmware data for storage. Once the valid data is extracted, it is written into the W25Q external flash memory using the OTA write function. The main purpose of the OTA write function is to write data into the external flash memory, but in this implementation, I have added additional verification checks to confirm whether the data has been written correctly. These additional checks may slightly increase the OTA writing time, but they help ensure that the firmware data is stored correctly and safely. If you prefer faster writing and do not require this verification process, you can simply comment out the section where the data is read back and compared after writing. That covers everything included in this file. Now, let us move forward and see how to implement these functions inside the application. Include the ESP8266 STM32.h file inside the project so that all the ESP-related functions and definitions become available in the application. Now, delete the application header section, as it is no longer required for this implementation, and removing it will keep the project cleaner. Inside the ESP source file, there is a variable named OTA active, which gets set whenever the OTA process is running. We need to access this variable inside the main file, so declare it as an external variable to allow it to be shared across different source files. Next, define a new variable that will be used to mark the start of the OTA process. The push button connected to the STM32 board will be used as a trigger for the OTA update, so whenever the button is pressed, this variable will be set to 1, indicating that the update process should begin. Now, define a custom write function to route the printf output through UART, which will allow us to see debugging messages on the serial console. Make sure to use the correct UART instance where the USB to TTL converter is connected, so that the logs appear properly on the connected terminal. When the program control enters the application, we will print the application version number for verification and debugging purposes. This version number will be extracted from the application header, which is written by the bootloader after the application is flashed into memory. Inside the main while loop, check whether the OTA begin variable is set. This variable will be set when the button is pressed, and once it is set, we will start the OTA update by calling the required OTA initialization function. Also, make sure to reset this variable after starting the OTA process, so that the function is not triggered again during the next loop cycle. As mentioned earlier, the function ESP OTA task must be called repeatedly inside an infinite loop to continuously process incoming OTA data, so we will place it inside a new internal while loop. In normal conditions, the application will continue running as usual without any interruption. When the button is pressed, the OTA begin variable will be set, which will start the OTA update process. At the same time, the OTA active variable will also be set to 1, and the internal while loop will continue running until the OTA update either completes successfully or fails. If the OTA update fails for any reason, the application will exit the OTA loop and resume normal operation. That completes all the required updates inside the main application file. Now, open the Flash script file. Since the application header section is no longer needed, delete that section to avoid unnecessary code. Also remove the additional section that we previously created for handling the application header. That completes the configuration for the application project. Now, open the project folder. Delete the OTA image.h file because it is no longer required in this updated workflow. The application binary file is already generated during the build process, and our Python script uses this exact binary file to create the final OTA image. Next, change the application version number so that we can confirm later whether the new firmware has been successfully flashed. Run the Python script, and it will generate a new OTA image.bin file, which will be uploaded through the TCP server during the OTA update. This is the server script, so copy it into the application project folder itself to keep all related files in one place. You can modify the server IP address and port number at the top of this script according to your system configuration. The server script searches for the OTA image.bin file, so make sure that the script is placed inside the same folder as this file. The server transmits data in chunks of 512 bytes at a time to ensure reliable data transfer. Initially, the server waits for a command from the client before starting the transmission process. It also waits for an acknowledgement message from the client after sending each chunk of data, and only then it sends the next chunk, ensuring proper synchronization. This completes all the configurations related to the application project. We will test and run everything together at the end. Now, let us move forward and modify the Bootloader project. The Bootloader already contains all the necessary functionality required to flash the OTA update successfully. Since the Bootloader now needs to retrieve the OTA firmware file from the external flash memory, we need to include the W25Q library files inside the Bootloader project. Now, open the Bootloader project inside STM32 CubeMX, so we can configure the required peripherals. Here, enable SPI1, which will be used to communicate with the W25Q external flash memory. Make sure that the SPI configuration is exactly the same as the configuration used earlier in the application project to ensure compatibility and reliable communication. Also, configure the PB0 pin as an output pin, because this pin is used as the chip select signal for the flash memory module. That completes all the required hardware configuration in CubeMX, so go ahead and generate the updated Bootloader project. Now, let us modify the Bootloader source code. First, delete the OTA image.h file that was generated and used in the previous parts of this series, as it is no longer required for this implementation. Next, include the W25Q header file so that we can use the external flash memory functions inside the Bootloader. Inside the main function, initialize the W25Q flash memory by calling the reset function, which prepares the flash memory for read operations. Let me also uncomment all the UART logging statements here, as they help in monitoring the Bootloader operation and debugging if any issue occurs. I have also removed the LED blinking indication for error conditions, since the UART logs already provide clear information about any errors that may occur during the process. Now, the Bootloader is fully capable of flashing the OTA update, but we need to modify the read function that is currently used to fetch firmware data. At the moment, this function reads the firmware data from the OTA image.h file, but in this implementation, we want the Bootloader to read the firmware directly from the W25Q external flash memory. So, instead of reading from the header file, we will call the W25Q fast read function to read the firmware data from the external flash memory. That is the only modification required here, so now go ahead and build the Bootloader project. Both the application and Bootloader projects are now ready, so let us flash them onto the development board. I will begin by flashing the Bootloader first, and for this, I am using the STM32 Cube programmer. Before flashing the Bootloader, let us erase the entire internal flash memory to ensure a clean start. Now, go to the programming section and flash the Bootloader ELF file into the microcontroller. The Bootloader flashing is complete. Now disconnect the SD link, because we will flash the application using the Cube IDE debugger. Open the application project inside STM32 Cube IDE and launch the debugger configuration. Here, create a new debug configuration for the project. Go to the Startup tab, and under the Start Address section, specify the vector table offset address, which corresponds to the starting address of the application in flash memory. After setting the correct start address, click Debug to launch the debugger session. Open the serial console to monitor the UART logs, and also start the TCP server script on the computer. Now run the debugger. At this point, the program control is inside the application, and the version number displayed is -1, because no valid data is currently stored inside the application header. Now, I am going to start the OTA update process by pressing the button. You can see that the OTA process has been successfully initialized. The server has started sending the firmware file, and the application is receiving and storing it correctly. The OTA update has now been flashed by the bootloader, and the program control has moved into the newly updated application. Let us understand the complete sequence of events, starting from the server side. The server was continuously listening on port 5678, waiting for a client device to connect. Once the client connected to the server, it sent a start command, indicating that it was ready to receive the firmware update. After receiving this command, the server began transmitting the update file in chunks of 512 bytes each to ensure reliable and controlled data transfer. Once the entire firmware file was transmitted successfully, the server closed the connection. Now let us look at the client side to understand what happened there. When the button was pressed, the client started by initializing the ESP module to prepare it for network communication. Next, the ESP module connected to the configured Wi-Fi access point and waited until it successfully obtained an IP address. After establishing the network connection, the client connected to the TCP server, initialized the external W25Q flash memory, and then sent the start command to the server. The client then began receiving data from the server and stored each received chunk into the W25Q external flash memory. In total, the client received 24,540 bytes, which matches the actual size of the firmware update file. Once the entire file was stored successfully, the client set the required update flag and then rebooted the system. After the reboot, the bootloader took control of the system. It detected the presence of the OTA update inside the external flash memory and started flashing the new firmware into the internal flash memory. Once the flashing process was completed and verified, the bootloader jumped to the application, and as you can see, the new version number is now printed on the serial console. The important advantage of this method is that the IDE is required only during the first flash. After that, all future firmware updates can be performed wirelessly without needing the IDE again. Let us test the process one more time to confirm everything is working reliably. In this new application version, the LED will blink every 1 second to show that the firmware has changed. Let us update the application version number to 6 and generate a new OTA firmware file. Now, start the server again and trigger the OTA update process by pressing the button. Sometimes, the OTA process may get stuck due to communication issues, but this will not affect the currently running application. In such cases, the application will continue running normally, and you can simply start the OTA process again. This time, the complete firmware file has been downloaded successfully, and the bootloader has flashed the new firmware as expected. The control is now inside the updated application, which is version 6. You can clearly see that the LED is now blinking every 1 second, confirming that the new firmware has been flashed successfully. So, we have successfully implemented and tested a fully wireless OTA update system. In the previous part of this series, we learned how to split the internal flash memory to store the OTA update inside the MCU's internal flash itself. In today's video, we used an external flash memory to store the downloaded firmware file before flashing it into internal memory. You can now choose or combine these approaches based on your project requirements and design preferences. For example, you may use internal flash storage with ESP8266 for simpler designs, or use external flash storage with Ethernet if you require larger firmware storage and higher reliability. That brings us to the end of this video. I hope the entire process was explained clearly and was easy to understand. All the files used in this video are available for download from the link provided in the video description. Feel free to leave a comment if you have any questions or doubts. Thank you for watching, and have a wonderful day ahead.